Acidification is one of those areas where climate change is often overlooked. So today I would like to talk to you and give you a little more information on ocean acidification and how it's impacting the environment today and how it will really impact the environment in the future. Ocean acidification is kind of a process where first fossil fuels are burned, and what that does is it releases CO2 gas into the atmosphere. The CO2 gas then is absorbed by H2O, and then it forms carbonic acid, which we can see up here. The carbonic acid then dissociates into H plus hydrogen and HCl3, and this overall will raise the acidity of the ocean. From there, it has one more proton or one more hydrogen, so it will then dissociate again into H plus and CO3 2 minus. Throughout this process, it leads to a raising of the acidity of the ocean, and this raising of acidity and this excess of HCO3 minus can have detrimental impacts on the ecosystems around. Since the Industrial Revolution, according to the Pacific Marine Environmental Laboratory, approximately 1/4 of all CO2 has been absorbed into the ocean. The increase in CO2 concentration leads to more carbonate ions in the ocean's waters. So again, according to the Pacific Marine Environmental Laboratory, here's a chart that I found on their website, and this really illustrates what goes on. First, you start with carbon dioxide and water. The carbon dioxide and water combine and form a carbonate ion. These carbonate ions and carbonic acids dissociate to form H plus and carbonate. The excess carbonate leads to calcium dissociating, which slows and ultimately halts the formation of calcium bicarbonate. And calcium bicarbonate is a large product in the formation of many seashells and other aquatic life forms. So here we can see that reaction, calcium and carbonate dissociating to calcium and CO2 minus 3. The excess acidity in the ocean means more H plus. This H plus then combines with the carbonate from the shells and forms bicarbonate, which is a hydrogen bonded to the carbonate ion. This really slows and halts the shells because without the shell's ability to form into calcium carbonate, it slows the growth and overall impedes the process. The decreased rate and overall change pH of the ocean has vast impacts on the biology of organisms throughout the ocean. In the present, since the Industrial Revolution began 200 years ago, really we've seen that the pH unit has decreased by more than 0.1 units. And this may seem like it's not a lot, but in actuality, the pH is a log-based scale, so small change is really tenfold in what it reveals about the environment. This equates to roughly a 30% increase in acidity according to Carol Tooley and Jean Gattus of the Science Direct. Then looking ahead into the future, the current rate of acidification is already 100 times greater than those measured before the Industrial Revolution. In the future, by 2050, it is predicted the pH to decrease by another 0.3 pH units, which would be approximately a 70% change in the pH. By the year 2100, the pH is expected to drop another 0.6 to 0.7 units to a rough 126.5% decrease in the pH from pre-industrial era. Since the industrial era has begun, the ocean has absorbed approximately 525 billion tons of carbon dioxide. So according to Smithsonian Ocean Portal, the increased bicarbonate ion concentration slows the growth of organisms which use carbonate for their shells. The impact of increased pH can lead to weaker shells of existing organisms, as we will demonstrate in our experiment. In cases such as corals, weakened shells can leave them as easy prey for sea sponges which burrow into coral. The pH additionally impacts fish, and slight changes can alter reproductive patterns. Just an idea for fish, approximately a change of 0.2 to 0.3 pH units in the human can cause seizures, coma, and even death in many cases. So a fish that is completely enveloped in an environment where the pH unit is changing from 0.1 to what is predicted to be 0.6 to 0.7 would be strongly impacted by this change in pH. Already we've seen that oysters have an inability to grow. Their larvae really develop shells at an early age, so this development of shells has been inhibited by this decreased pH. And we've seen massive die-offs in the US Pacific Northwest due to over-harvesting, so it's really a twofold process. The social impacts, really there's a whole list of social impacts. Anything affecting the ocean is really a worldwide phenomenon. According to Carol Tooley and Jean Gattuso, some of the main areas we would see extreme social impacts would be food resources. Large quantities of seafood are required to sustain many of the populations of this planet. The previous examples really list how one small change in the food chain, such as coral, could really affect biodiversity as a whole. Ocean acidification impacts the ecosystems as a whole, limiting resources for humans. Another huge area that could be affected is tourism. In places like the Great Barrier Reef, coral die-offs from the change in temperature and attacks from sponges due to the change in pH has caused a lot of destruction of these organisms. Oftentimes, many of the communities are based on these coral reefs and ocean-based attractions. The impact on the economy can create an increase in the poverty rate of people in those areas. As far as recreation goes, organisms such as jellyfish actually thrive in more acidic seawater. In recent experience, beaches have been forced to close due to jellyfish booms, which are mainly due to the increased pH and the increase in temperature. The experiment. Okay, so here at Mount Union in analytical chemistry, we conducted an experiment to analyze the effects of increased CO2 on the pH, as well as its impact on shells in the water. So the University of Mount Union, we conducted a 3-week experiment to better help understand this process. We used artificial seawater for the experiments and shells collected by our instructor from natural sources. After letting the solution stir on a plate for a week, we analyzed different various aspects of them to determine how great the extent of acidification and calcium carbonate breakdown was observed. So in our week 1 through 2, really what we did was we titrated a solution with HCl. The HCl then gave us a good idea of how much carbonate was existing in the total solution. And what we found was actually the carbonate levels were undetectable, but there was a large change in bicarbonate along with increased acidity. So we determined that with CO2 pumped directly into our artificial seawater, there was a 1.92 pH units change, and this was an increase in acidity or decrease in overall pH. After pumping the CO2 through, we then calculated the percent increase of bicarbonate in each of our samples. In the non-carbonated sample, it was 3.49% increase. And since the pH of our water was a little more acidic than seawater, this result is expected. But then overall, the increased acidity of the carbonated led to a 11.39% increase in the concentration of bicarbonate. And over here, we can see those ratios. We have the molarity of our bicarbonate in our original solution versus the molarity in our non-carbonated solution and our carbonated solution. And really what these illustrate is you can see a direct increase between our artificial control and our CO2 treated seawater. Week 3 of the lab, we really focused on titrating with EDTA. EDTA is a complexing ion that forms with 2+ ions for complexation. So initially what we did was we treated our seawater with EDTA, and we measured the total amount of 2+ ions that were impacted by it. Next, we did a titration with EDTA where we added hydroxide, and the hydroxide ion actually bonds with the magnesium to give it a total charge of +1. By weeding out the magnesium ion, we could then directly determine the amount of calcium ion present in our solutions, both before and after carbonation. So the table you see over here shows the mass of the shells. In addition to our titrations, we also observed the mass of the shells both before we treated them with the seawater and after we treated them. Before, we could see that the mass was here, and then after, we could see that there was a total percent loss of mass in the non-carbonated of 0.162%. This could be attributed to user error really extracting the cell. Also, we could expect a little breakdown due to the slightly more acidic seawater than we see in nature. The carbonated version had a percent loss of 5.43%, a much greater percent relative to the 0.162. And these calculations were determined after only 1 week of the carbonated shell mixture being placed on a stirring pad. So you can imagine over time that these changes would be much greater. The amount of calcium in solution can be seen on this bottom chart here. We determined our concentration in the original to be 0.0737 molar of 2+ ions. Our calcium concentration after was 0.0167 molar. So using this 0.0167 molar as a baseline, we were able to determine the percentage increase in calcium in both samples. The relatively low increase in the non-carbonated could be due to our finely ground particles, where the 36.5% increase shows that the carbonated solution actually has a huge impact on the breakdown of calcium bicarbonate. Interpretations of these results. The results really all point towards pH having a direct impact on the bicarbonate or the calcium carbonate breakdown in seawater. The amount of CO2 seemed to show that there was a higher amount of calcium carbonate disintegration in our seawater samples. So the next real question is, how can you get involved? And really, I feel since you have such a strong stance on environmental issues, this could be one issue that you could draw light to. With so much of the world at risk for this, it's really important now that we take action. And even if we stopped our production of carbon dioxide, there would still be so much in the atmosphere that it would continue on until equilibrium was reached. The easiest solution for a government party is really just to encourage citizens to be conscious about their decisions and the production of CO2 and burning of fossil fuels. Transportation, fuel-efficient power, and energy are all areas that the average American can work on in order to improve the amount of CO2 in the atmosphere. Without taking the proper steps, the decrease in carbon emissions worldwide, we could see issues over resources, tourism, and really everywhere if these problems aren't addressed. The current rate of acidification has never been seen in history, so even predicting how detrimental all this could be to society is kind of hard to make that prediction, because right now we have nothing to compare it to. Thank you, President Gore, and I really do hope you focus on this issue and draw light to it in the political spectrum. Appreciate it. It's good enough.
President Gore.
Yeah, I know. I ended on a low note, but like I'm starting to feel it. And when I got out there, my mouth got really fucking dry.